out in space. Okay? So this is nothing spectacular, but it's spectacular compared to what happens on Earth. The pulsar rotational period will increase over time due to the release of electromagnetic radiation, which doesn't change its radius but reduces its rotational energy, and also it's emitting gravitational waves as well. Okay, so what is the angular momentum of the pulsar? Okay, so no, it's just losing energy via electromagnetic. Okay, suppose the angular velocity increases at a rate of 10 to the minus 14 radians per second square. So it's slowing down, okay? And its angular velocity decreases at that rate. What is the torque on the pulsar? Okay. So I'm going to erase all of this. Okay. So again, in a pulsar, what needs to happen? So this is a very dense object. Again, the sun is almost 1,000,000 times as massive as the Earth. And this neutron star, which is more massive than the sun, is only from here to Ormond Beach. Yeah. So here is the spin axis, and here is the magnetic axis. Okay. And what happens is it's emitting radiation along this axis. And so if it's spinning like that, and if its radiation axis is like this, it's emitting radiation like that. So it's like a lighthouse. And if we happen to be in its line of sight, then we can see it. And what this has a period of 33 milliseconds. What that means is, so every 33 milliseconds, you're seeing that beam. Okay? And since it's losing energy, it's slowing down. And now you're seeing that beam later and later. Okay? So that's what that means. All right. So what is the angular momentum of the pulsar? Again, I won't okay, angular momentum of the pulsar is I times omega. I is the moment of inertia, omega is the angular speed. And for a solid sphere of uniform density, there is the moment of inertia. And what is omega? It's the angular speed, 2 pi over t. Okay? So this is 33.5 milliseconds. This, you know the mass of the pulsar, which is that, radius of the pulsar, which is 10 kilometers, so you can calculate that. Okay? I won't put the numbers. You guys can do that. Suppose the angular velocity decreases at the rate of 10 to the power of 14 radians per second square. Okay, torque is I times delta omega by delta t. Okay, so to calculate the torque that is slowing it down, there again you have those numbers, and you have this number. That number is that number. Okay. So so you plug in those numbers and you can calculate this. What's the? Did you guys understand that? Yep.
When did you get the change in angular speed at the time?
That's this. They give you that.
Oh.
Yeah. All right, I will calculate this just to you guys, somebody want to look up the torque on your truck or on a truck in Newton meters. So I'll calculate this. Okay, that's 10 to the 8, 38, minus 1424. Okay, so this is the torque that is slowing the neutron star down because it's losing energy. What is the? Did you look up the?
The heavy duty truck, it's
Hmm?
about 1400.
What?
For a heavy duty truck, it's like 1400.
Newton meters. Okay. So torque is on a truck is about 10 to the 3 Newton meter. Okay. So a billion trillion times greater than that. Yeah. Okay, the blades of a wind turbine are 30 meters long, so 30 meters is roughly the width of this room. This is actually now a small wind turbine. Now they're building turbines with blades over 100 meters long. Rotate at a maximum rotation speed of 20 revolutions per minute. If the blades are 6,000 kgs, that's probably the weight of a Hummer, each, and the rotor assembly has 3 blades, calculate the angular momentum of the turbine at this rotation rate. Okay. The moment of inertia of one blade so if you look up the moment of inertia of a blade about, so here's the blade and you're calculating the moment of inertia about the end of the blade, and that's 1/3 ml square. 1/3 ml square. Okay. And so the moment of inertia of the windmill about that axis is 3 times that. It has 3 blades. It's ml square. And what is, if the blades calculate the angular momentum is times omega. Okay. So, and omega is 20 revolutions per minute, 20 into 2 pi radians divided by 60 seconds. Okay, so 2/3 pi radians per second. All right, so L, the angular momentum is ml squared 2 pi over 3. L is 30 meters. Okay, so that's the angular momentum. Okay, again, so this kind of stuff will be useful because if the blades are rotating and the weather is going to get bad, you want to stop the blades. You don't want the blades rotating during hurricanes and stuff like that. Okay, so you apply brakes, lock them up. And then what is the torque required to rotate the blade up to the maximum rotation rate in 5 minutes? So if you want to speed it up in 5 minutes, torque is delta L by delta T. Okay, so you want to go from 0 to that value in 5 minutes. Okay. Did you guys understand that? Five minutes is that many seconds. And that'll come out in Newton meters, so okay, so again, you saw that for a big truck, the torque is 1400 Newton meters, so the torque of 30 trucks, 27 trucks. And this is a small windmill. So this problem says a merry-go-round has a radius of 2 meters and a moment of inertia of 300 kg. Okay, so here's the top view of the merry-go-round. It's rotating about that point. Its moment of inertia is 300 kg. Okay, so a buoy of mass 50 kg runs tangent to the rim at a speed of 4 meters per second and jumps on. So this buoy is running tangent to it and jumps on. Okay. So when he jumps on, all the forces, so this is a collision. You guys remember in lab, in a linear collision, what is conserved? I'm sorry? Linear momentum is conserved. Okay, so here's an angular collision. Here's a collision where there's no torque involved. So angular momentum is conserved. Okay. So this is the initial configuration. The angular momentum is the angular momentum of this guy, which was spinning, and the angular momentum of the kid. Okay. And then he jumps on, and what will happen? This is the final angular momentum. Okay. And so this is the initial angular speed, that's the final angular speed. Angular momentum is conserved. Okay. So a buoy of mass tangent to the rim at a speed 4 and jumps on. The merry-go-round is initially at rest. So initially at rest, what is the angular momentum after the buoy jumps on? So this is, so initial angular momentum is just, okay, so the angular momentum of the buoy is his linear momentum times this distance, the moment arm, okay? So it's 0 for the merry-go-round plus mass of the buoy times velocity of the buoy times the radius of the merry-go-round. Okay. So it's this momentum times the moment arm. That's what it boils down to. So this is 0 plus 50 kgs plus velocity of the buoy, radius 2 meters and 4 meters per second, 2 meters. So 100, 400 kg meter square per second. So that is the initial angular momentum of this system, okay? And so after the buoy jumps on, the angular momentum of this system should equal this. Now the moment of inertia of this guy, of this system is the moment of inertia of the buoy plus the moment of inertia of the merry-go-round, and the moment of inertia of the merry-go-round is given, okay? So what is the final moment of inertia? Is 300 for the merry-go-round plus mass of the buoy times the radius of the merry-go-round square. 300 plus mass of the buoy. What is the mass of the buoy? 50 kgs. And the radius is 2 meters. So that's 200, so 500 kg meter square. So L final will be I final times omega final equal to L initial. So the angular momentum of the merry-go-round will be equal to that cancels with that. It's 1/2, and radian is a free label. Okay. So this thing will rotate at 0.8 radians per second. Okay. And you guys understand that the faster you jump on, the faster this will rotate. Okay. What will happen if you jump straight at the axis? Nothing. It won't rotate. Okay. If you come straight at the axis, this will be 0. Initial angular momentum will be 0, and you won't rotate. All right. So this is an interesting problem. A space station consists of a giant rotating hollow. Okay. Okay. So if you're going on a circular path, so if you're going in a circle, what makes you go in a circle? A centripetal Yes. Okay, so you have centripetal acceleration, all right? Um, so, so if you go in a circle, something has to push you in that direction. Okay? When you're standing on the ground is pushing you up because there's gravity. Okay? So, in the future, a space station consists of a giant rotating hollow cylinder of mass 1,000,000 kgs. Okay, so spacefarers, they'll be going in a space station that is a hollow cylinder like this. Okay, and it'll be rotating like that, and everybody will be living inside there. Okay, so when you're rotating like this is pushing you down, and then you'll have everything will be living in here, soil will be there, roots will grow in that direction, and so on. Okay. So what you have to do is, so if you're going to the next star, you're going for 6 months or so on. You're living there, and what do you want for gravity? 9.8 meters per second squared. So you got to make sure that this thing rotates at the appropriate speed. Okay. Okay. So a space station consists of a giant rotating hollow cylinder of mass 1,000,000 kgs. So you're going to launch 1,000,000 kgs. Okay. This would not have been possible without reusable rockets that Elon Musk has built. Back in the day, I don't know, it used to cost, the launch cost per pound has decreased by over a factor of 100. So if it used to cost $100 per pound, I'm not sure, again, now it's $1 per pound. Yeah. So that's why reusable rockets are very good. Yeah. So this is 1,000,000 kg, including the people on the station, and a radius of 100 meters. So this is like, this cylinder is like from here to mainland High. So that distance is from here to mainland High. Okay. It is rotating in space at 3.3 revolutions per minute. Okay. In order to produce artificial gravity. Again, so centripetal acceleration is 9.8 meters per second. If 100 people of an average mass of 65 kg spacewalk to an awaiting spaceship, what is the new rotation rate when all the people are off the station? So the people get in a spaceship and they go away, and so now the moment of inertia is decreased, and so it'll rotate faster. Yeah. So again, this is a collision problem again. Yeah. So So okay, so initially when all the people are there, everything is at a distance of r. So the initial mass times r squared, and the final moment of inertia is final mass times r squared. So initial mass is, what is the initial mass? 10 to the power 6 kgs, including all people. And 100 meters is the radius. So that's 10 to the power 4, 10 to the power 10 kg meter square is the initial angular momentum. And final angular momentum is, what is the mass? 1,000,000 kg minus 100 people. So 6,503 kg. So that is, oh. Okay, so that's the new moment of it. Oops. That's the new mass times radius squared. So you see, it's that is 1%. That's reduced by 0.65%. The mass of the thing is reduced by that much, and so the moment of inertia is reduced by that much. Okay, so what we have is, when they go away, angular momentum is conserved. So omega final is I initial over. So it'll speed up by that amount, by 0.65%. That's 10 to the 10 divided by 0.9965 into 10 to the 10 times omega initial. And so this is 1 divided by 0.9965 omega initial. So the new angular velocity is 1.0035 times initial angular velocity. Okay, so if this was 1, then it would have increased by 1%. So the angular speed has increased by 0.35%. Okay, so the change in angular speed is 0.35%. It's sped up. And what happens when those guys come back? Yeah. And they have to come in radially to slow down. Okay? Because remember, if they come in like that boy on the merry-go-round, tangentially it'll spin. Okay. So, all right. Anyway, so that's the future. That's how you build space stations. And you can grow stuff and all that kind of stuff. All right. It's 1:50.